You are watching a man make a mistake right now. Somewhere in Vietnam, in the Philippines, in Indonesia, a farmer just finished harvesting his banana bunch, grabbed his machete, and cut the trunk down to the ground. He will chop it into pieces. He will throw it to the side of the field, maybe feed it to the pigs, maybe just let it rot in the sun. He does this every single time because that is what you do with a spent banana plant. Everyone knows that. It is obvious. It is common sense. Except 4,000 kilometers away, in a drought-stricken village in Bangladesh, another farmer just dug a trench 2 feet deep beneath his vegetable beds. He is placing those exact same banana trunk pieces, carefully, side by side, into the ground. He covers them with soil. He plants his crops on top. And then for the next 90 days, while the dry season burns everything around him, he barely touches his watering can. Here is what those two farmers do not know about each other. And here is what almost nobody in modern agriculture will tell you, because there is no product to sell you, no subscription to sign up for, no equipment to buy. That banana trunk the first farmer just threw away, it is 90% water. A single trunk weighing 10 kilograms holds 9 liters of moisture locked inside a structure so perfectly engineered that it releases that water slowly, silently, directly into the root zone of whatever plant grows above it for months. This is not folklore. This is cell biology. And by the end of this video, you will never look at a banana plant the same way again. Let's talk about the business of thirst. The global irrigation equipment market was valued at $9.5 billion in 2023. By 2030, analysts project it will cross $14 billion. That is not a coincidence. That is a business model. And the business model is simple. Your plants need water, you need a product to deliver that water, and somewhere between your garden hose and your vegetable bed, there is a company making sure you never stop buying. Walk into any agricultural supply store today, and the message is the same. Drip irrigation kits for a small home garden, $50 to $80. Polymer hydrogel crystals, the kind that swell up and release moisture slowly, $20 per kilogram, with instructions to reapply every season. Moisture-retaining ground fabric, weed barriers with humidity control built in, $15 to $40 for a single raised bed. And if you want the premium smart irrigation system with soil sensors and a phone app that tells you exactly when your tomatoes are thirsty, that starts at $120 and the sensors need replacing every 2 years. Every single one of these products is solving the same problem that a banana trunk buried 2 feet underground also solves, for $0. Now ask yourself, when was the last time you saw a YouTube ad for a banana trunk? When did a garden influencer do a sponsored post about crop residue you already own? When did a university extension program publish a glossy brochure explaining how to bury something you were going to throw away anyway? The answer is never. And the reason is not because the technique does not work. The reason is because a technique that costs nothing cannot fund a marketing budget. It cannot sponsor a podcast. It cannot pay for a booth at a trade show. In the economy of agricultural knowledge, the information that survives is the information that someone can profit from distributing. Everything else gets quietly left behind. This is what happened to banana trunk burial. Not banned, not disproven, just unprofitable to remember. And it goes deeper than marketing. The green revolution of the 1960s and 1970s, that sweeping transformation of global agriculture that saved millions from famine, came packaged with a worldview. High-yield seeds, chemical fertilizers, mechanized irrigation, it worked. Genuinely, remarkably, it worked. But the implicit message embedded in every training program, every agricultural college curriculum, every government extension service was this: the old ways are primitive. The new ways are scientific. If your grandfather buried banana trunks in his field, that was subsistence ignorance. Now we have drip tape and NPK ratios. Move forward. An entire generation of farmers was taught to be embarrassed by what their parents knew. And a $9.5 billion industry was built in the space that embarrassment created. The question is not whether modern irrigation has value. It does. The question is what we agreed to forget in exchange for it. and whether anyone ever asked your permission before making that trade on your behalf. To understand how this knowledge got buried, in the bad way, the forgotten way, you have to go back further than the Green Revolution. You have to go back to a time when the relationship between a farmer and a banana plant was not transactional. It was not harvest the fruit, discard the trunk, move on. It was something closer to a philosophy. In the river deltas of what is now Bangladesh and West Bengal, farmers have been cultivating bananas alongside food crops for at least 2,000 years. The banana was never just a fruit tree in this tradition. Every part of the plant served a purpose in a closed-loop system that modern agronomists are only beginning to rediscover with expensive research papers in peer-reviewed journals. The leaves were used for mulching, for wrapping, for ground cover during dry spells. The flowers were eaten, the root suckers were replanted, and the trunk, the pseudostem, as botanists call it, was either fed back into the soil directly or used to line irrigation channels, where it would slowly weep moisture into the surrounding earth for weeks. This was not written down in any formal manual. There was no agricultural ministry producing pamphlets about it. It lived in the hands of farmers, in the seasonal rhythms of villages, in the kind of knowledge that gets passed from a grandmother to a granddaughter while they work in the field together at 5 in the morning. Ethnobotanists who have spent decades documenting traditional farming practices in South and Southeast Asia consistently report the same thing. Banana residue management was so deeply embedded in local farming culture that practitioners could not always explain why they did it. They just knew that fields where banana trunks had been buried produced better crops through the dry months. That was enough. Move westward across the Indian subcontinent to the state of Rajasthan, one of the driest inhabited regions on Earth, where annual rainfall in some districts barely reaches 300 millimeters. Here, farmers developed what researchers now call indigenous water harvesting techniques out of pure necessity. Buried organic material was a standard component of field preparation in many communities. Not banana specifically in all cases. The specific material varied by what was locally abundant. But the underlying principle was identical. Pack the subsoil with high moisture organic matter before the dry season begins. Let capillary action do the rest. This concept was not unique to one culture or one climate. It was independently discovered across centuries by farming communities from sub-Saharan Africa to the highlands of Central America, wherever the gap between rainy season and dry season was wide enough to be deadly. The tragedy is not that this knowledge existed. The tragedy is the precise moment it began to disappear and how fast it went. In 1943, a catastrophic famine swept through Bengal, killing an estimated 3 million people. The causes were complex: wartime grain export policies, speculation, deliberate mismanagement by colonial administrators. But in the aftermath, the political conclusion drawn by planners in both London and Delhi was simple. Traditional agriculture cannot feed a modern population. It is too fragile, too dependent on weather, too inefficient. What followed was decades of institutional pressure to modernize, to replace ancestral farming practice with chemistry, machinery, and centralized water infrastructure. By the time the Green Revolution arrived in full force in the late 1960s, the replacement was nearly complete in many regions. Farmers who had once known exactly how to work with their local ecology were now enrolled in government training programs, teaching them to read soil pH charts and calculate fertilizer application rates. The knowledge of what to do with a banana trunk after harvest was not forbidden. It was simply never mentioned again. It fell out of the curriculum, out of the extension service handbooks, out of the agricultural university syllabi. Within 2 generations, it had become invisible. There is a particular kind of loss that historians of science call tacit knowledge extinction. It refers to the disappearance of skills and practices that were never written down. Knowledge that existed only in the doing of it, in the physical memory of people who are no longer here to show you. The burial of banana trunks for subsoil moisture retention is, in most of the world, a textbook case of tacit knowledge extinction. It did not die because it failed. It died because the system that replaced it had no mechanism for preserving what it was discarding. And here's the detail that makes this story more than an agricultural footnote. In the villages of Bangladesh, where this practice quietly survived, not because anyone protected it, but simply because those communities were too poor and too remote for the Green Revolution to fully reach. Researchers from the Bangladesh Agricultural Research Institute began documenting measurably different outcomes in the early 2000s. Fields where traditional organic burial techniques had been maintained showed significantly better moisture retention during dry season stress periods. The crops were not just surviving. In some trial comparisons, they were outperforming chemically managed plots during drought conditions at a fraction of the input cost. The knowledge had not degraded in the ground, it had been waiting. Before we go any further, we need to cut open a banana trunk. Not metaphorically, literally, because once you see what is actually inside that structure, the science of everything that follows becomes not just believable, but inevitable. Pick up a freshly cut banana trunk, and the first thing you notice is the weight. A mature pseudostem from a standard Cavendish or plantain variety will run anywhere from 8 to 15 kilograms. That is heavy for something that looks from the outside like a solid green cylinder. But when you make a clean cross-section cut with a sharp blade, the interior reveals something that stops most people cold the first time they see it. There is no solid wood. There is no fibrous core the way you would find in a sugar cane or a bamboo stalk. What you see instead is a series of concentric rings, layer after layer of tightly wrapped leaf sheaths, each one separated from the next by a thin membrane, each one composed of cells so saturated with liquid that the cut surface glistens immediately on contact with air. This is the pseudostem, and the word pseudo, false, is the key to understanding everything. A banana plant does not have a true stem in the botanical sense. What you see above ground, that column that can grow 3 to 8 meters tall and support a bunch of fruit weighing 30 kilograms or more, is entirely constructed from the overlapping base sheaths of successive leaves. Each new leaf grows from the center, pushing outward, wrapping around all the leaves that came before it, building up this layered cylinder from the inside out over a period of 9 to 12 months. The cells that make up each sheath layer are called parenchyma cells. And parenchyma cells are, in the vocabulary of plant biology, essentially storage units. They are large, thin-walled, and filled almost entirely with a central vacuole, a fluid-filled cavity that can occupy up to 90% of the cell's total volume. In the banana pseudostem, these cells are packed so densely with water-based cellular fluid that the tissue as a whole reaches a moisture content of 88 to 93% of fresh weight. To put that in terms you can hold in your hands, that 10-kilogram trunk you're about to throw away contains, conservatively, 9 liters of water. Not surface moisture, not dew. Water locked inside living cells, held there by osmotic pressure, released only when the surrounding environment creates the conditions for release. Now here is where the physics becomes remarkable. When you bury that trunk in soil that is already moist, as it would be at the end of a rainy season, the osmotic pressure inside the parenchyma cells and the moisture pressure in the surrounding soil reach a rough equilibrium. The water stays inside the cells. The trunk just sits there, heavy and saturated, doing almost nothing. This is critical because it means the trunk is not dumping its water into the soil immediately. It is not creating a bog. It is holding its reserve in a stable state, waiting. Then the dry season begins. The topsoil loses moisture first, through evaporation, through plant uptake, through the simple physics of warm air pulling water upward. As the soil moisture content drops around the buried trunk, a gradient forms. High moisture concentration inside the parenchyma cells, lower and lower moisture concentration in the surrounding soil matrix. Osmosis and capillary action respond to gradients. Water begins to move, slowly, passively, without any pump or pipe or timer, outward from the cells into the spaces between soil particles. The rate of release is governed by the steepness of the gradient, which means it is self-regulating. The drier the soil gets, the stronger the pull. The more moisture the trunk releases, the more the gradient moderates, the slower the release becomes. It is a biological feedback system of extraordinary elegance, and it costs exactly nothing to operate. Root systems discover this moisture source within days of planting. Roots are not passive structures waiting for water to come to them. They grow directionally toward moisture gradients, a behavior called hydrotropism. As the buried trunk begins its slow release cycle, the chemical and moisture signals it sends into the surrounding soil act as a beacon. Fine root hairs extend toward the trunk, make contact with its outer layers, and in many cases penetrate directly into the softening outer sheaths as decomposition begins. The plant is not just benefiting from the ambient moisture in the soil, it is, in a very real sense, drinking directly from the trunk. Researchers measuring soil moisture profiles in plots with buried banana pseudostem have recorded moisture retention figures that are difficult to achieve even with commercially installed drip irrigation systems operating on time cycles. A 2018 study examining organic matter burial techniques in tropical smallholder farming systems noted that high moisture organic substrates placed at 30 to 60 centimeter depth consistently maintained measurable moisture gradients for periods of 60 to 120 days post-burial under dry season conditions without any supplemental irrigation during the measurement period. 120 days, 4 months, from a 10-kilogram piece of plant material that was already in your field, waiting to be thrown away. The engineering industry spent decades and billions of dollars trying to replicate, with plastic tubing and electronic sensors and polymer chemistry, something that a banana plant does with its own body by default. And the most unsettling part of that sentence is not the money, it is the word decades. Because the farmers in Bangladesh were not waiting for a research paper. They already knew. But here's the thing about the banana trunk that nobody tells you. The water is not even the most valuable part. Most people who encounter this technique for the first time fixate on the moisture retention. The 90% water content, the slow release capillary mechanism, the months of passive irrigation. And that is understandable because that is the dramatic number, the one that stops you mid-sentence when you first hear it. But if you are only thinking about the water, you are reading the first chapter of a 2-chapter story and closing the book early. Because what happens after the water is gone is, in certain ways, even more significant than the water itself. Let us talk about what a banana pseudostem is actually made of, beyond the fluid. The dry matter fraction of a banana trunk, the structural material that remains after you account for all that water, is composed primarily of cellulose and hemicellulose fibers, lignin in relatively low concentrations compared to woody plants, and a mineral profile that is, from a soil chemistry perspective, extraordinarily generous. Independent analyses conducted across multiple agricultural research institutions in South Asia, Southeast Asia, and East Africa have consistently documented the same basic mineral composition in banana pseudostem dry matter. Potassium, expressed as K2O, ranges from 3.2 to 4.8% of dry weight depending on variety and growing conditions. Calcium runs at approximately 0.9 to 1.2%, magnesium at 0.3 to 0.6%, phosphorus at 0.2 to 0.4%, and nitrogen, while modest at 0.3 to 0.5%, is present in organic form, meaning it releases slowly and continuously rather than in the sharp spike and crash cycle of synthetic nitrogen fertilizers. Now translate those percentages into something concrete. A single banana pseudostem with a fresh weight of 10 kilograms contains approximately 1.1 to 1.4 kilograms of dry matter after the water is accounted for. Apply the potassium percentage to that dry matter figure, and you arrive at somewhere between 35 and 67 grams of potassium oxide equivalent per trunk. A standard commercial application rate for potassium sulfate fertilizer in vegetable production is roughly 150 to 200 grams per square meter per season for potassium-demanding crops like tomatoes, peppers, and cucumbers. 1 kilogram of potassium sulfate from an agricultural supplier in Vietnam or the Philippines currently retails for approximately $1.50 to $3, depending on grade and source. You are bearing the equivalent of meaningful, measurable, agronomically significant potassium fertility into your soil for free every time you bury a trunk instead of burning it or feeding it to livestock. But the numbers, as compelling as they are, miss something important about how this potassium behaves once it enters the soil system. Synthetic potassium fertilizers, potassium chloride, potassium sulfate, potassium nitrate, are water-soluble salts. They dissolve rapidly when wet, release their potassium ions into the soil solution in a concentrated burst, and create a brief window of high availability followed by a longer period of leaching loss, particularly in the sandy or well-draining soils common across tropical Southeast Asia. Apply too much at once, and the salt concentration around the root zone rises to the point where it actually pulls water out of root cells rather than allowing uptake, a condition called fertilizer burn, which can set a plant back weeks or kill young seedlings outright. This is why commercial fertilizer application requires careful timing, measured dosing, and often multiple split applications across a growing season. Potassium released from decomposing banana pseudostem does none of these things. It releases slowly, in step with the rate of microbial decomposition, which is itself governed by soil temperature and moisture, the same conditions that govern plant growth. When the soil is warm and moist and plants are growing rapidly, decomposition accelerates, potassium release increases, and nutrient availability peaks exactly when plant demand peaks. When conditions cool or dry, decomposition slows, release moderates, and the remaining mineral reserve sits protected within the organic matrix until conditions favor growth again. This is what soil scientists call synchrony, the alignment of nutrient release timing with plant uptake demand. And it is one of the central goals of sophisticated precision agriculture systems that cost thousands of dollars to implement. The buried banana trunk does it automatically, for free, governed entirely by the same environmental signals that the plant itself is responding to. And below the chemistry, there is ecology. A decomposing banana pseudostem buried in warm tropical soil becomes, within 2 to 3 weeks of placement, one of the most biologically active microhabitats in your entire garden. The combination of high moisture, abundant carbon from cellulose breakdown, and diverse mineral content creates ideal conditions for explosive growth in fungal networks, bacterial colonies, and the microfauna that feed on them, including, critically, earthworms. Earthworm populations in agricultural soils are one of the most reliable indicators of long-term soil health, and they are notoriously difficult to attract and retain in heavily tilled, chemically managed plots. But give them a buried organic mass with the moisture profile and carbon content of a banana pseudostem, and they will find it. Multiple studies on organic matter burial in tropical systems have documented significant earthworm aggregation around decomposing high-moisture plant material within 30 days of placement. And wherever earthworm populations concentrate, soil structure improves. Their castings increase aggregate stability, their tunneling improves drainage and aeration, and the enzyme-rich mucus they secrete as they move through the soil accelerates the very decomposition process that is releasing your potassium and building your humus. The buried banana trunk does not just feed your plants. It rebuilds the living ecosystem beneath your feet. It converts dead organic waste into a self-sustaining cycle of moisture, fertility, and biological activity that continues long after the original material has completely disappeared. What started as 9 liters of passive irrigation water ends, 4 to 6 months later, as a column of biologically enriched, potassium-loaded, earthworm-cultivated soil that will outperform chemically managed beds in the seasons that follow, without a single additional input. The commercial agriculture industry has a name for this kind of integrated, self-reinforcing soil improvement system. They call it regenerative agriculture, and they charge consultants significant fees to implement it on large farms using certified compost, inoculant products, and precision organic fertilizer blends that can cost $800 to $2,000 per hectare per season. You have been throwing the same result away every time you harvested a bunch of bananas. Let me ask you something directly. When you started watching this video, how did you think of yourself? Probably as someone looking for a gardening tip. Maybe a cheaper way to water your plants through the dry season. A practical trick, a small optimization, a minor upgrade to what you are already doing. That is a reasonable expectation. That is what the thumbnail promised, and that is what most gardening content delivers. A technique, a hack, a workaround. Watch the video, take the tip, move on. But somewhere between the Bangladesh farmer who stopped watering for 90 days and the research paper documenting 4 months of passive moisture release and the potassium chemistry and the earthworm ecology, something shifted. or it should have. Because what we have been talking about for the last 20 minutes is not a gardening tip. It is a lens. And once you look through it, it is very difficult to look away. Here is what that lens shows you. Every time you stand in a garden supply store holding a $20 bag of slow-release fertilizer granules, you are holding a product that exists, in significant part, because someone successfully convinced your grandparents that what they already knew was not good enough. The slow-release mechanism on that bag, the thing you are paying for, is a polymer coating designed to do what organic decomposition does naturally. The potassium inside it is refined from mined ore, processed in an industrial facility, packaged, shipped, marked up at 3 different points in the supply chain, and sold to you as a solution to a problem that a buried banana trunk was already solving before the factory that made that fertilizer existed. You are not an uninformed consumer who needs better products. You are the inheritor of a knowledge system that was deliberately pushed to the margins because it could not be monetized. And the first act of reclaiming that inheritance is simply knowing that it exists. This is the identity shift that matters, not from beginner gardener to expert gardener, from consumer to custodian. And this is where the story becomes personal in a way that no research paper can capture. Think about the farmers who kept this knowledge alive. Not in journals, not in university archives, not in any form that the modern agricultural system would recognize as legitimate. They kept it alive in the only way tacit knowledge can survive, by doing it season after season in villages remote enough that nobody came to tell them they were doing it wrong. They were not heroes. They were not activists preserving indigenous wisdom against colonial erasure, though that framing is not entirely inaccurate. They were mostly just people who could not afford to forget. People for whom the difference between bearing a banana trunk and throwing it away was the difference between feeding their family through August and not. There is a particular kind of intelligence that only poverty can preserve. Not because poverty is good, it is not. And romanticizing subsistence struggle does no one any favors. But because when you have no margin for error, when there is no agrochemical supply store within 50 kilometers and no credit to buy from it anyway, you pay attention to your land in a way that prosperity makes optional. You notice that the plot where the banana grew last year holds moisture longer than the plot next to it. You ask your mother why. She tells you what her mother told her, and the knowledge survives another generation, not because anyone decided to protect it, but because it was too useful to abandon. The farmers in the well-resourced regions, the ones who received the Green Revolution first and most completely, they are the ones who lost it, not because they were less intelligent, because they were given the option to outsource their memory to a supply chain, and they took it the same way most of us have outsourced our sense of direction to a phone and can no longer read a roadmap. The question this raises, and it is the question I want you to sit with for the rest of this video, is not whether you should bury banana trunks instead of buying drip tape. You might need the drip tape. The two things are not mutually exclusive. The question is deeper than that. It is about what you believe your relationship to your garden actually is. Are you a customer of the agricultural supply industry, dependent on its products to translate your intentions into outcomes? Or are you a practitioner of something older and more resilient? Someone who understands the underlying systems well enough to work with them directly, with whatever materials the land itself provides? Because here's the truth that $14 billion irrigation market does not want you to internalize. The land has already solved most of its own problems. It has been solving them for 10,000 years of human agriculture and for hundreds of millions of years before that. Our job was never to replace those solutions with purchased inputs. Our job was to understand them well enough to work alongside them. You are not a consumer of gardening products. You are the custodian of a living system that knows things you have not yet remembered. That is who you are in this story, and that changes everything about what comes next. Now I need to tell you something that most content in this genre refuses to say. This technique is not magic. It is not a universal solution. It is not going to work equally well in every soil, every climate, every planting context. And if I stood here and told you it was, I would be doing exactly what the fertilizer companies do when they print guaranteed results on the back of a bag without mentioning the 14 variables that determine whether those results actually materialize in your specific garden. So before you go outside and start digging, You need to understand the conditions under which banana trunk burial underperforms, fails quietly, or actively creates problems. Because there are real ones, and pretending otherwise would waste your time and potentially damage the beds you're trying to improve. The first and most significant limitation is soil texture. The capillary moisture transfer mechanism we discussed in Part 4, the slow passive movement of water from the saturated trunk cells into the surrounding soil matrix, depends on that surrounding soil having enough fine particle content to maintain capillary tension. In clay-heavy soils and loamy soils, this works beautifully. The fine particles create a dense network of microscopic channels through which water moves by surface tension, drawing moisture outward from the trunk in the steady controlled release that makes this technique valuable. But in coarse, sandy soils, the kind common in coastal regions, in riverbeds, in areas where the topsoil has been heavily eroded, and what remains is essentially coarse mineral substrate with minimal organic matter. Capillary tension is weak. Water moves through sandy soil primarily by gravity, not by surface tension, which means the moisture from the trunk tends to drain downward rather than moving laterally and upward into the root zone. You will still get some benefit from the potassium, fertility, and the biological activity as the trunk decomposes. But the moisture retention effect, the primary reason most people try this technique, will be significantly diminished. If your soil is predominantly sandy, you can partially compensate by mixing generous quantities of compost or fine organic matter back into the trench fill before planting, which increases the fine particle content immediately surrounding the trunk and improves capillary function in that zone. A thick surface mulch layer of rice straw, dried leaves, or grass clippings will also help by reducing evaporation from the topsoil, which decreases the overall moisture demand on the subsoil reservoir. These are not perfect solutions, but they extend the technique's effectiveness into soil types where it would otherwise struggle. The second limitation is crop selection. Not everything you might want to grow benefits from a consistently moist subsoil environment. Mediterranean herbs, rosemary, thyme, oregano, lavender, are adapted to dry, well-drained soils and will develop root rot or fungal issues if their root zone stays persistently moist through the growing season. Cacti and succulents are obvious non-candidates. Garlic and onions, which need a dry down period in their final weeks before harvest to properly cure their bulbs, can be problematic if planted directly above an active trunk section that is still releasing moisture at bulbing time. Root vegetables like carrots and parsnips grown in heavy, moisture-retentive conditions can develop forked or misshapen roots as they push through overly compact wet subsoil. For these crops, either skip the banana trunk preparation entirely or plant them in raised beds or sections of your garden that are separate from the buried trunk zones. The technique is optimized for moisture-demanding, warm-season crops. Tomatoes, peppers, eggplant, cucumbers, squash, beans, corn, leafy greens, and most tropical fruit trees. And it performs best for precisely the crops that struggle most in dry season conditions. Match the tool to the task. The third limitation is timing asymmetry in continuous production systems. If you are running a garden that produces year-round through multiple successions of planting, which many home gardeners and small-scale market growers in tropical climates do, the banana trunk system creates a timing constraint that can be awkward to manage. The trunk is most effective when buried fresh, at the beginning of the dry season, and it reaches peak decomposition and potassium release roughly 4 to 6 months later. If you need to replant the same bed 2 or 3 times within that window, you are working around a buried organic mass that is at different stages of decomposition with each successive planting. In practice, this is manageable. You replant in the same position, the roots of successive crops continue to benefit from both the residual moisture and the ongoing fertility release, but it does mean you cannot easily till or deeply cultivate that bed without disturbing the trunk material and releasing whatever moisture reserve remains in an uncontrolled way. Plan your bed layout accordingly. Treat any bed with buried trunk sections as a no-deep till zone for at least one full season. The fourth limitation, and this is the one I most want you to take seriously because it is the one with genuine consequences if ignored, is disease transmission from infected planting material. I mentioned Panama disease briefly in the action section, but it deserves more weight here. Fusarium oxysporum cubense, the fungal pathogen responsible for Panama disease, is a soil-borne organism that can survive in infected soil for 30 to 40 years without a host plant. It spreads through infected plant material, contaminated soil, water movement, and farm tools that have contacted infected plants without being cleaned. Tropical Race 4, the current strain devastating commercial Cavendish plantations globally, has been detected in multiple Southeast Asian countries, including Vietnam, the Philippines, Indonesia, and Malaysia. If you are sourcing banana trunks from outside your own property, from markets, from neighbors, from unfamiliar sources, you are introducing a potential vector for soil contamination that could make your beds inhospitable to bananas and certain other crops for decades. This is not a reason to abandon the technique. It is a reason to be disciplined about sourcing. Use material only from plants you know are healthy, plants you have observed through their full growing cycle, with no yellowing, no wilting that cannot be explained by drought stress, no browning of inner sheaths. If you have any doubt about the health of a trunk, do not bury it. The benefit of the technique does not outweigh the risk of introducing a persistent soil-borne pathogen into beds you intend to farm for years. The fifth and final limitation is one of scale and expectation management. A single banana trunk buried under a 2-meter bed will meaningfully extend the moisture retention of that bed through a moderate dry season. It will not transform a desert into a productive garden. In regions experiencing severe multi-year drought, with annual rainfall below 400 millimeters and prolonged dry seasons exceeding 6 months, the technique provides useful supplemental moisture buffering but cannot replace irrigation entirely. In these conditions, banana trunk burial works best as one component of a layered water management strategy, combined with deep mulching, rainwater harvesting, strategic shade management, and careful crop selection, rather than as a standalone solution. What I have described in this video is a tool, a remarkably effective, zero-cost, ecologically sound tool with a 2,000-year track record in the hands of farmers who understood their land intimately. But like every tool, its value depends on using it correctly, in the right conditions, with honest expectations about what it can and cannot do. The farmers who developed this technique were not naive optimists who believed a banana trunk could solve every problem their land presented. They were careful, attentive practitioners who knew exactly when and where to apply it, and equally importantly, when not to. That discernment, that calibrated context-sensitive intelligence, is as much a part of the knowledge as the burial technique itself. Inherit the whole thing, not just the trick.